So good evening everyone. Today is our eighth lecture on the for the tutorial session of NPTEL course Algebra 1, and in this lecture, lecture 8, we will be doing some assignments from uh, module theory, and at the last we will be doing some problems from exterior and tensor algebras. So let us start with some problems from module theory. So notations and abbreviations I will first be telling you. So we denote R by a ring, and with unity it's better, and M unital R module, that means 1 dot M equals to M on R, and for every M belongs to M. So okay, so since you are learning about module and its examples, so let us start with the easiest of exercises. Let R be a ring with 1 R, and let M be a left unital R module prove that for all small m belongs to capital M, 0 dot m equals to 0 and minus 1 of m equals to minus of m. Now proof of this theorem, this exercise is quite simple if you are familiar with if you have done kind of similar problems in ring theory and group theory. Anyway, let us start solving this. Let small m belongs to capital M. Now 0 dot m plus 1 dot m equals to 0 plus 1 dot m is to 1 dot m by the definition of module. Now since M is an abelian group, subtracting 1 dot m from both sides, we have 0 dot m equals to 0. Now note that 1 dot m plus minus 1 dot m equals to 1 minus 1 dot m is to 0 dot m is to 0. So by uniqueness of the inverses in a group, minus of m equals to, so 1 dot m is to minus of. So we are done. Now for the next problem, since you are already familiar with group action and we have done some exercises from group action, so I thought maybe this question will be useful for you. Let capital R be a ring with one R and let M be a left unital R module. Prove that the restriction of the module operator dot, that is scalar multiplication tool, R cross, that means the set of ring minus the zeroth element to this, is a group action operator on the group of units in R. So what does it say actually? That is that if M is a left uniter R of a module over R, we have to show that the this action, that is from R star M to M by R dot N goes to Rn, is a group action. So we will solve this. So I will give you 5 minutes to try, and we will be starting with 6:15. Okay. So I'm sure you have guessed it till now. So let us do this one. Yeah. So yeah, recall that R star is indeed a group. Right? It is a group under multiplication. Certainly, the restriction of dot to cross M is a mapping cross N to N, right? Now, for all small m belongs to capital M, we have 1 dot n equals to n, and if u comma v is to r star, then uv dot n equals to u dot v dot n. So r star acts on M by the restriction of our module operator. Right? So you are done. Now, for the third question, we are getting familiar with the properties, defining properties of the module over a ring. So I think in this class it is it is right that we go with the base problems first, and most of these problems are from Damit food, so you can also look in there for any reference or any theorem or any proof. Let R be a ring with R, and let M be a unital R module. Suppose smaller of capital R and small f of capital M with M not equals to 0, such that R dot M 0. Prove that R does not have a small r does not have a left inverse in capital R. Solution. So so we first start with a claim, that is, let M be a unital left R module. Uh, then for all R belongs to capital R, we have R dot 0 equals to 0. But this is straightforward, right? I mean, uh, if you still want to prove this, note that this is from the 0 element is from M, so that is why I will be doing its solution. So proof small, so R dot 0 plus R dot M equals to R dot 0 M plus M equals to R dot M. So from the right cancellation property, you see that this implies that R dot 0 M equals to 0 M. Now suppose there exists small s belongs to capital R such that small a small r equals to 1. Now M equals to 1 dot M, that means SR dot M equals to S dot R dot M equals to S dot 0 equals to 0. A contradiction. Hence, no such left inverse exists. So for the next problem, we will be dealing with a particular subset of a module, and we have to show that this is a sum module. Okay. I am not writing down what is R because I have been repeatedly writing it, so I just ignore it. So let your n is a natural number, so naturally it is greater than equals to 1, and let m equals to Rn. Recall that capital M is a left R module via the action R dot AI to RAI. Let I of k, where k runs from 1 to n, be a family of ideals of small r. Prove that the following subsets Rn are some modules. So the first one is n equals to product of k equals to 1 to n I k. So this is a sign for standard sign for product, and the second one is n to ai of Rn such that sum of ai is 0. So okay, so think it for 5 or 6 minutes, then we'll be again discussing this problem. Bolo.
Content creator.
আবার ফোন কর। মিলনদা ফোন দিচ্ছে না। শিবের একটা ফোন করতো। ফোন ধরছে না। শ্রীপতি তুই ল্যাবে আছিস রে? একটা পূজার একটা ডেলিভারি এসছে নিবি রে? ও ও কি যাচ্ছে? ও তাহলে তুই ছেড়ে দে, ও কাউকে একটা পেয়েছি, ছেড়ে দে। হ্যালো, না না না, ও অভিপসা যাচ্ছে বললো, ছেড়ে দে। ঠিক আছে, হ্যাঁ দেখি। So okay, let us do the solution now. So we will use the sum module criterion. Let us write it. Sum module criterion, that is for S, a subset of M, is a sum module if and only if S1 minus R dot S2 belongs to S for every S1 S2 belongs to S, and for every R belongs to R. So exactly like the subring criterion, if you can remember. So now, so for the part 1, let us look at the solution. Now note that 0 belongs to the sum module, the subring ik for each k, right? Then 0 belongs to the product of ik, hence the product ik is non-empty. At least 0 is there, right? Now suppose ai comma bi belongs to this product of ik, and let small r belongs to capital R. Now small r belongs to capital R. Now because each ik is an ideal, we have that ak plus r dot bk belongs to ik for each k, right? Because it is an ideal also, so this is true, and also this is a subring. Then ai plus r dot bi equals to AI RBI belongs to product of IK. Thus K is a submodule of M. Now for the second part, certainly we have the sum of zero elements is 0, right? So equals to 1 to n. So 0 belongs to n, right? Again we will use the sum module criterion. So now suppose we have AI BI belongs to n. Then sum of AI equals to sum of BI equals to 0, and let small r belongs to capital R. Then sum of AI plus r of sum of BI equals to sum of AI dot r dot BI equals to 0, that is AI plus dot BI I running from 1 to n belongs to n. Thus n is a sum module of n. Now we will be doing a similar another problem. So this will be our question number 5. Let M be a left R module and let R be an ideal. Define IM equals to summation of small k belongs to capital K, AK dot MK, AK belongs to I and MK belongs to capital M, and also mod k is finite. Prove that IAM is a submodule of M. So again you should try this first and then we will be doing its solution. So first note that uh, 0.0 equals to 0, which belongs to Im, so that Im is non-empty. Now let summation of capital K dot Mk, and let Bl dot Nl belongs to Im, and let small r belongs to capital R. Then the sum of K dot Mk plus R dot Bl dot Nl equals to K dot Mk plus Bl dot Nl belongs to Im. So this implies that Im belongs to M is a sum module. So now let us move to our next problem. Question number 6, that is, let R be a ring and let M be a left R module. Let MT small t, where small t belongs to capital T, be a family of left R modules of M with your capital T is non-empty. Prove that the arbitrary intersection is a sum module of M. So again, you can think this for 2 or 3 minutes, then we can start discussing this. Okay, so let us do this uh, solution. Note that uh, for all small t belongs to capital T, we have 0 belongs to empty. Now because uh, capital T is non-empty, we have 0 belongs to intersection of n small t, where small t belongs to capital T. Now suppose a comma b belongs to intersection of mt and small r belongs to capital R. Since each small m capital T is a sum module, we have a plus rb belongs to mt for all small t belongs to capital T, and thus we have that a plus rb belongs to this. So using the sum module criterion, this intersection mt belongs to n is a sum module. Okay, now we'll be introducing a new kind of object which is pretty much interesting. So this will be our question number 7. Let R be a ring and M be a left R module. Let N is a sum module. We define the annihilator of n in R to be a n n R n equals to small r belongs to capital R such that R dot capital N equals to 0. Now prove that annihilator of R of n is a two-sided ideal in capital R. So you are seeing a new kind of object that is called annihilator of a sum module, and so in this exercise you will be seeing that this is indeed a two-sided ideal, and if you take R to be a commutative ring, then you will be seeing that this is an ideal. So again you should try this for yourself and for 2 or 3 minutes, and let us start after that. Okay, so let us do the solution. uh, so we need to show uh, that a annihilator of n is non-empty closed under subtraction and absorbs R from both sides, because we want to show that uh, it is a two-sided ideal. So let small n belongs to capital N and a comma b belongs to annihilator of R n. Then we have a minus b small n equals to a dot n minus b dot n is to 0 minus 0 equals to 0, so that we have a minus b equals to annihilator of Rn. Now let small n belongs to capital N. Let small a belongs to R and let small r belongs to capital R. Note that RA dot n equals to R dot A dot n equals to R dot 0 equals to 0, and AR dot n equals to A dot R dot n equals to 0, so that we have RA comma AR belongs to annihilator of R n. So this shows us that this shows us that is a two-sided ideal in R. Now, since we have seen annihilator, so let us see another kind of element, that is called a torsion elements in a module. So let R be a ring with unity which is again non-zero, and let M be a left R module. An element small m belongs to capital N is called torsion if there exists small r belongs to capital R such that r dot m equals to 0. We define torsion of M is the elements of M which such that r dot m is 0 for some non-zero r of r. So you are getting what I am saying is that unlike the previous thing, here the condition is changed. That is, there you are seeking ideals of of the elements consisting such that the product with the sum module is 0, but here we are seeking elements from the module such that r dot m equals to 0 for some elements from R, which are again non-zero also. So we will be proving couple of things. First of them is if R is an integral domain, that means it has no non-zero divisor, non-zero zero divisor, then this torsion sum module of a module, actually we have to prove that it is a sum module first of M. So this set is a sum module, we can say it like this. Now the second one, show by an example that if R is not an integral domain, then torsion mod set need not be a sum module. Actually, let us forget it right now. First do this problem. So we can do this first. Try to understand the definition and see if you can prove this one. Then step by step we will be doing other problems. Okay, so let us start solving this uh, proof. Note that one dot zero equals to 0 in n, so that 0 belongs to torsion of n. Now suppose AB belongs to torsion of n and small r belongs to capital R. There exists non-zero u comma v belongs to capital R such that u dot a equals to v dot b equals to 0. Now since capital R is an integral domain, we have u dot v not equals to 0. Now uv dot a plus r dot b equals to u dot equals to v dot u dot a plus r dot v dot b to 0. Since r is commutative, okay, let me write it. Since r is commutative, so that we have a plus r dot b is to n, thus tau n is a submodule of n. Now we have a second question, that is, we have to show that if R is not an integral domain, then this submodule thing may not be true. Okay, so see, think if you can think of an example. Okay, so let us uh, do the solution of this. Find the uh, counter example. uh, Consider the ring sorry Z6, that is zy6z. So here 2.3 equals to 0, so it is not an integral domain. And consider m equals to r, that is consider z6 as an z6 module, as a left module over itself. So as a left module over itself, note that neither 2 bar nor 3 bar are 0 in R, but 3 bar dot 2 bar equals to 2 bar dot 3 bar is to 0. Thus we have 2 bar comma 3 bar belongs to tor of m. However, 2 bar plus 3 bar equals to 5 bar, and r dot 5 bar equals to 0 only if r equals to 0. So this is pretty easy, you can check yourself. Thus tor n is not a submodule of m, as it is not closed under addition. So we are done. So next we will be doing our third problem in this tor set. Prove that if R has 0 divisors, then every non-trivial R module has non-zero torsion elements. So again, you should think of its solution for 2-3 minutes, then we will start doing it. Okay, so let us start with the solution. Suppose uh, R has 0 divisors and let M be a left R module. Suppose by way of contradiction that tau of M equals to 0. Now let small r smallest be non-zero such that r is equals to 0 and let small m belongs to capital M be non-zero. Now small r smallest m is to r s dot m is to 0 dot m is to 0, so that s dot m is torsion. Thus s dot m equals to 0 and so m equals to 0, a contradiction. Thus every non-trivial R module contains non-zero torsion elements. So we are done. আর একটা ডেলিভারি এসেছিলো বলে ফোন করছিলাম, নেওয়া হয়ে গেছে। হ্যাঁ হ্যাঁ বুঝেছি হ্যাঁ ঠিক আছে। Now since we are short on time, let us do some problems from tensor algebra and symmetric products. So you know, in a tensor algebra, that is your so let us do I think we can do this problem. So number 9 I guess. Yeah. Let R be a commutative ring, that means A dot B equals to B dot A with 1 R, and let M be a free R module such that R M equals to MR. Prove that kth exterior power that means it's, it's antisymmetric is a free R module of rank. Okay. So the proof is quite rigorous. Um, so so let us start doing this. Suppose solution, suppose E equals to E is a free generating set of N, is a free generating set of N so this is convincing that the kth tensor power this is denoted by this is free M is free with free generating set your EI1 tensor up to EIK, where your I goes from K to N. Now first we will construct a generating set for your exterior power. I mean, it is clear that your exterior power of M is generated by the set of all simple K tensors M1 of Mk, because this is a surjective map from tensor product to your exterior product. So yeah, so the generators goes to generator. Note that by multilinearity we may assume that each Mi comes from the free generating set E, say EI1 exterior up to EIK. Moreover, we may assume that I1 less than to Ik. We claim that these are all distinct. I mean, to see this, uh, for each increasing choice function, lambda going from k to n, define phi lambda from tk to r. So say this is my tensor. This is my tensor power. So tk to r, by letting ejk tensor up to ejk equals to sigma, where if image of j so this is psi of sigma, where sigma is the, I mean, if image of j is a permutation of image of lambda namely the unique permutation sigma and 0 otherwise, and we extend linearly. So certainly for increasing choice functions, lambda, your AKM belongs to phi of lambda, so that we have an induced homomorphism tensor power k m to r. Moreover, phi lambda is 0 on all of the ei1 exterior up to eik except the one whose indices are given by lambda. Thus, the elements of generating set are distinct. There are k distinct ways to choose ij. So we have a generating set B of exterior power k of m of order nk. Note that any non-trivial linear combination linear combination in the free basis on tk. Thus our gen set is free, so we are done. So today we have done problems from both module theory and exterior algebra. So in the next class we will be dealing with more on module problems. So please send me an email if you have any doubts, or you can post it in the common group. Now okay, so good night everybody.